Hello, welcome to another lecture. This is a lecture for Module 2. If you turn your page to page 37, you'll see Module 2 is one-dimensional motion, equations, and free fall. So you'll remember in Chapter 1 last time was all on one-dimensional equations, and we went over the basic equations for velocity, for calculating velocity, and for calculating acceleration. Module 2 extends those equations, and we're going to derive three main equations. So, if we start with chapter 2, page 37, the basic equation that we start with in this chapter is acceleration equals a change in velocity divided by a change in time. Now, you'll remember, just for review, that if we're in the metric system, the velocity, the units of velocity will be in meters per second, divided by time is in second. So that gives us meters per second squared. Okay. Now, you will remember from last module that whenever you see a delta symbol, that a delta symbol means, for instance, with a delta V for delta velocity, whenever you see delta, it means the initial, it means the final minus the initial. So delta V is defined as the final velocity minus the initial velocity. And likewise, delta time will be defined as the final time minus the initial time. So what we have is we have two different times. We have, if this axis, x-axis, is a time axis, and the y-axis is our velocity axis, we have an initial time, t initial, and then we have a final time, t final, and at one particular time we have a certain velocity. We'll call it V initial. V initial. And at this time, we have another velocity, which is the final velocity. And we draw a straight line between the two. And the definition of the acceleration is the slope. The slope is defined as the change in velocity over the change in time. Notice that if we think of this as a y-axis and this is an x-axis, this is exactly the same as the slope. The change in y over the change in x, which is the slope. So this is really just a review of Chapter 1, but this is our starting point for Chapter 2. So, one of the assumptions in Chapter 2, in fact, there's two main assumptions that all the equations are derived with in Chapter 2. And they are, number one, that the acceleration is a constant. Acceleration is a constant. Which means, for instance, that if you think of it from a slope point of view, that this acceleration here is a constant slope. Constant slope. So if you think of it from a graphical point of view, all of these equations that we're going to go over in this chapter assume we have a constant slope. If we plot velocity versus time. The other main assumption that we're going to use in this chapter is that the motion is linear, or in a straight line. The motion, all the motion is in a straight line. Another way to say this is it doesn't curve. In other words, if the initial velocity is going in a certain direction, it stays in the same direction. It doesn't curve. So there's no curving of the motion. Now, why would this be? Think about it this way. Suppose I draw things in x, y, and the motion starts this way, but then it curves and it goes this way. Well, this is motion. When you change direction, we're changing from one dimension into two dimensions. We'll get to two dimensions, but that's in chapter 3 and 4. So we're just not there yet. So right now, all of the equations in this chapter, we're only going to deal with motions in a straight line. We will deal with curved motion later on in two dimensions, but that's in a couple of chapters. So these are the two main assumptions in this chapter. The acceleration is constant slope of the constant acceleration, and the motion is in a straight line. Okay, now notice that when I'm going to clean this up just a little bit. Notice in this case, whenever we have constant acceleration like this, because this slope is constant, from this point to this point, we have a straight line, we can also talk about an average velocity. And that's very important in this chapter. I'm going to just clean this up a little bit. Here's the initial velocity, and here's the final velocity. Right in the midpoint of these two times, right in the midpoint, in fact, I'm going to make this in red. Right in the midpoint, I'll call this T midpoint. Right in the middle of these two times, this time and this time, that corresponds to what I'm going to call the average velocity. Okay? The average velocity will be simply the average of these two velocities. It will be the initial velocity plus the final velocity divided by 2. Okay? So one of the characteristics of all of these problems that we're going to work in this chapter is that not only can we talk about an initial velocity, we can talk about a final velocity, but we can also talk about the average velocity. And this is a very key point that we'll come back to over and over again in these problems. So the average velocity actually occurs at the midpoint of the time. So notice that T, in fact, we can certainly call it just T average. The average time is also the initial time plus the final time, all divided by 2. Okay? So it turns out that all of the equations in this chapter can be derived quite nicely with these two equations. Okay? So now, if you take your book, we're on page 37. We go over to page 38. Flip over to page 38, and they derive an equation, which we're gonna derive also right now too. Okay, let's look at this equation, but instead of talking about the final time and the initial time, the initial time, we're going to leave the time just as delta t. Delta t. So we'll talk about the initial velocity and the final velocity, but the time duration we're just going to call delta t. Okay? Let's take this equation, which is acceleration equals the final time, which I'll abbreviate, minus the initial time divided by delta t. Let's solve, using algebra, let's solve this equation for the final velocity. I'm going to multiply both sides by delta t. I get a delta t equals the final velocity minus the initial velocity. Now I'm going to move this to the other side. I'm going to add plus delta of v initial to both sides. And I'll get a delta t plus v initial equals v final. Okay? So I'm going to rewrite that up here. I'm going to put this there, v final on the left side. The final velocity equals the acceleration times, I'll do it this way, the initial velocity plus the acceleration times delta t. Okay? Now, let's say, if we let delta t start at 0, we can simply say that the final velocity is the initial velocity plus acceleration times time. Where here, what the idea is that t starts at 0 and it goes up to some particular time. Okay? So we're just simply going to allow delta t just to be replaced by t. And that shouldn't make any confusion, I hope. If you look at this, what actually do we have? If we flip this around just a little bit more, at plus vi. Think of this in terms of y equals mx plus b, okay? Where we have the t is like the x-axis, time is down here. The y-axis is like v, okay? And the y-intercept here is the initial velocity. That's the initial velocity. And the final velocity is here. And there's a slope. Whoops. So, at time equals 0, the velocity is equal to the initial velocity. At some later time, t here, the velocity is equal to the final velocity. And notice that the slope is equal to the acceleration. Okay? So I'm going to put over on the left-hand side here this equation. The final velocity equals the initial velocity plus acceleration times time. Okay. And over on this side, I'm going to put the other equation, which we were talking about, which is that the average velocity, the average velocity is equal to the initial velocity plus the final velocity divided by 2. Okay? Now, if you look on page 38, in fact, you will see that this equation is actually, they derive this equation right on page 38 and over to 39. Now, in the book, they call the initial velocity v naught. I should say v naught. They call it v naught. So, but just to make it clear, in my discussions here, I'm just going to simply call it vi for v initial. Okay. Down here at the very last paragraph in the text, right before example 2.1, it reads this. This will be the general philosophy for this course when it comes to derivations. If I present, that is the author, if the author presents a derivation, you should try to understand it, but you should not be expected to reproduce it or any of the equations in it. The only thing you will be expected to really remember is the final result and how to use it. So don't worry if a few of my derivations go over your head. Well, as I tell all my students, strike that paragraph out of your book. I don't like it. Because actually, you should be able, all these derivations that I do and all the derivations that the author does, you should be able to reproduce it. As a matter of fact, when it comes to the lab and special questions on the lab, I will ask you to do just that. So, actually, in physics, derivations are very important, and when you go, if you go further into engineering and further into physics and even further into chemistry, learning how to derive equations, especially some of the important equations, is very important. You will be tested on it in college, so you better get used to it now in high school. So, so if these derivations go over your head, you should worry, actually. Sorry to tell you that, but you should worry. And, however, with the appropriate algebra and geometry that you should already know, you should be able to successfully handle these derivations. So if at first they seem a little hard, keep on working at it, because hard work will aid you and will aid your understanding. And so don't believe the author when he says these derivations are not important. They are important. Pay attention. Okay, having said that, notice even the author goes on to page 40 and 41, and he derives an equation on page 41. And then if you go on further, he derives an equation on page 44 and 45 and 46. He derives another equation at the bottom of page 46. And then he gets to page 47, where he lists a table of equations, and there's 5 equations. The first equation is this equation, which we had in chapter 1. The velocity is a change of distance over change of time. The second equation is the acceleration is a change of velocity over change of time. We've had that equation. The third equation is actually this equation right here. The initial velocity, the final velocity is the initial velocity plus acceleration times time. The fourth and the fifth equations are the one that he derives. And they are, and I'm just going to write them down now, the final velocity squared equals the initial velocity squared, and here I am going to go back to his v naught, plus 2 times a times delta x, and delta x equals the initial velocity times time plus 1/2 at squared. Okay. At this point, instead of going over how the author derives these two equations, I'm going to go over a slightly different way. And I hope the way that I go over it will actually be more clear. So, what we're going to do is we're going to briefly go over something that's not exactly in the book, but something that actually derives these two equations in a more clear way. But these two equations are derived. These two equations are derived from these two equations. Almost these two equations. Let's go back to this equation here. Notice that if we have an average, if we have an average velocity, that is, we have an initial velocity and a final, we add them up, we divide by 2, and that gives us our average velocity. You will remember from chapter 1 that the displacement distance is equal to the velocity times the time. Okay? So, what that means is this, that we can also do this. Since we have an initial velocity and a final velocity, and we're ramping from an initial velocity up to a final velocity, and we can talk about an average velocity, we can take that average velocity and plug it into here, and we can say that the average velocity times the time is equal to the distance traveled. Okay? That's an important concept. In other words, you can actually think about it this way. Suppose you're starting off in a car. Here's your car. And you're traveling a certain distance, and you start off slowly at 0 miles per hour, and over the course of 1 hour, you accelerate continually but very smoothly from 0 on up to 60 miles per hour. And it takes you exactly 60 minutes or 1 hour to do this. You start off at 0 and you slowly accelerate very uniformly, so that by the time you start off at 0, by the time you get to 1 hour, you're at 60 miles per hour. Notice at exactly the midpoint, which is 1/2 an hour, how fast are you going? You're going 30 miles an hour, right? You're going 30 miles an hour right in the middle. Well, if you want to calculate how fast you went, since you start off at 0 and you uniformly ramped up to 60, we could say, well, on average, I'm traveling 30 miles an hour. During this half of the time, I was under 30 miles an hour. On this half of the time, I was over 30 miles an hour, but these two halves cancel out. And so the distance I traveled would be 30 miles per hour times 1 hour, and I would have a distance of 30 miles. So in 1 hour, I would have traveled 30 miles. Okay, that's clear? So, this will hopefully convince you that we can talk about average velocities, and that we can use these average velocities for calculating the total distance traveled during that length of time. Okay? So, I can come in here and say that the distance traveled is equal to the initial velocity plus the final velocity, all divided by 2, times the time. All I did here is I took the definition of the average velocity and I plugged it right into here. Okay? So I'm going to come up here and I'm going to write this equation right up here. The distance traveled is equal to the initial velocity plus the final velocity, all divided by 2, times time. So at this point, we have two equations. We have this equation here, which, by the way, is equation 2.6 in the textbook. And then we have this equation, which, by the way, is equation 2.10. 2.10 in the textbook. Okay. Now, over here, what I'm going to do is I'm going to take these two equations. Notice that both equations have the final velocity in them. There's a final velocity here, and there's a final velocity here. Now, over here, what I'm going to do is I'm going to eliminate, I'm going to solve these two equations, and I'm going to eliminate the final velocity from both equations. Okay, so how do I do that? I take well, one way is I can do this. Notice I have a final velocity here is equal here. I'm going to take this equation and I'm going to substitute the final velocity right into here. So I'm going to take the second equation, x equal the initial velocity plus, and in place of the final velocity, I'm going to substitute this expression here. So I'll have the initial velocity plus acceleration times time, all divided by 2 times time. So you notice what I did. This expression here is simply the final velocity, which I substituted this for. Okay? So now notice I have how many initial velocities? I have initial velocity plus an initial velocity. So I have 2 initial velocities plus AT times T all divided by 2. Okay. I'm going to multiply by the T, and I'll have T multiplied by this term and multiplied by this term. I'm going to put the 1/2 out here. Well, no, I'll just keep it down here. See, can you all see this? I think you can. 2 VI times T plus AT times T, or T squared, all divided by 2. I'm going to come up here. Well, I'll come right over here. And I'm going to say x equals, now I'm going to divide by 2. So this 2 cancels out 2, and I get the initial velocity times time plus 1/2 AT squared. So you'll notice that this equation here, x equals the initial velocity times time plus 1/2 times 1/2 times AT squared. That is equation, that's equation 2.19 in the textbook. Okay? And I think this is a much clearer way to derive it than what's presented in the book. You're simply taking these two equations and you're solving them together and you're eliminating the final velocity. Notice in this equation here, you have x, you have the initial velocity, time, acceleration, but there's no final velocity in this expression. Why? Because you eliminated the final velocity from these two equations. Okay, so hopefully that's clear. So now what we're going to do, I'm going to erase this, and we're going to solve these two equations in a slightly different way. Okay, now what we're going to do is, this time we're going to eliminate t from both equations. Notice this equation has a time in it, t, and this equation has a time in it also, a t. Okay, so we're going to solve these two equations but eliminate t, the time. Okay, so what's one way to do that? Well, let's take this equation and let's solve it for